you guys, you give me the energy to come here. It's end of the night, kind of tired. It was a hard day. But I said, let's come for these people who are crazy. But I'm not gonna make this session very intense. It will be more kind of a chill vibe. We are gonna watch, you know what I'm gonna watch, some machine learning videos by Andrew Ng. And last time we talked about decision trees, about the skiing, latitude, seasons, Canada, yes, no question, and we had this, oh, and then every note was again, oh. So, oh my god. Let's go, guys. Let's go and enjoy the rest of session 10. We are getting there, guys. We have 20 sessions. We got it halfway through. We made it together. And it was already easy. Even decision trees that, woo! They're like what are they called? Multi-formula functions? Something like that. Crazy. Isn't it amazing? These are autumn 2018. 6 years ago. Wow. And these videos got views. Oh, by the way, look, guys. Before getting into the video, I want to show you a curve that we need to look. First video, 2.5 million. Second video, 1 million. Third video, 500,000. Fourth, 250,000. Again, 250,000. 200, 150, 100. So many people in 8 sessions. How many people they lost? Like 100. I mean, not so many people kept up watching the videos. Well, maybe not all of them were applicable, but a lot of people quit. A lot of people quit. We ain't one of those. Look, now we watched even video which is below an hour. Okay, interesting. This video was actually very boring and it got like 70. Okay, again it went up 130 because decision trees was exciting for me. It was new concept, so it got more, again more, then went down. Andrew brought it up again. Andrew collapse 70. This video got 40k. Guys, only 50k people made it to the last video. I'm saying not all of them. Some of them said, okay, we only need this part of the video already. But a lot of people left. Are we going to be like them or are we going to finish? I say we are going to finish. We are going to finish this deal, and then we land of opportunities open to us. Horizon is infinite. Decision trees make our decisions easier and fruitful.
And then search through that linear route. And it turns out that that yields you an optimal solution.
Let me see if you have me. Oh.
So decision trees, we can use them for regression. We can also use them for categorical variables. one thing that I've not gotten into is that you can imagine that in the limit, if you grew your tree without ever stopping, you could end up just having a separate region for every single data point that you have. And so that's really, you could consider that probably overfitting if you ran it all the way to that completion, right? So you can sort of see that decision trees are fairly high variance models.
Oh, decision trees are high variance.
And so one thing that we're interested in doing is regularizing these high variance models.
DT.
And generally how people have solved this problem is through a number of heuristics.
Down
Okay? So one such heuristic is that if you hit a certain minimum leaf size, you stop splitting that leaf. Okay?
Sport.
So for example, in this case, if you've hit like you only have 4 examples left in this leaf, then you just stop. Another one is you can enforce a maximum depth.
What was a leaf? Wait a minute.
And sort of a related one in this case is a max. You can only hit a number of heuristics, okay? So
Leaves should be final nodes? Yeah.
one such heuristic is that if you hit a certain minimum leaf size, you stop splitting that leaf, okay? So for example, in this case, if you've hit like you only have 4 examples left in this leaf, then you just stop.
Depth.
Another one is you can enforce a maximum depth.
I told it, guys. I knew it. It's easy. If I said it,
Related one in this
I know
case is
everybody
max
can say it.
number of nodes.
Maximum nodes. Number of nodes. Well, that is kind of
And then a fourth
mix
very
of
tempting one, I've got to say,
depth
to
and
use
width,
is you
right?
say a minimum decrease in loss, right?
I don't get that.
Right? And I say this one's tempting because it's generally not actually a good idea to use this minimum decrease in loss one. And you can think about that by thinking that if you have any sort of higher order interactions between your variables, you might have to ask one question that is not very optimal or doesn't give you that much of an increase in loss, and then your follow-up question combined with that first question might give you a much better increase. And you can sort of see that in this case, where our initial latitude question doesn't really give us that much of a gain. We sort of split some positive and negatives, but the combination of the latitude question plus the time question really nails down what we want. And if we were looking at it purely from the minimum decrease in loss perspective, we might stop too early and miss that entirely. And so a better way to do this kind of loss decrease is instead you grow out your full tree and then you prune it backwards instead. So you grow out the whole thing and then you check which nodes to prune out. Pruning. And how you generally do this is you have a validation set that you use this with, and you evaluate what your misclassification error is on your validation set for each example that you might remove, or each leaf that you might remove. So
I didn't get it quite.
You would use misclassification in this case. With the validation set.
What is the validation?
Any questions?
I just asked.
Yep. The minimum decrease in loss? So, yeah, of course. So you'll recall that before I was talking about sort of this RP, this loss of R parent versus loss of R1 plus loss of R2, right? So when I had written out a maximization, basically. To be clear, the question is, can you explain a little bit more clearly what this minimum decrease in loss means? And so you have your loss of R1 and R2 versus your loss of R parent, right? So the split, before the split, right, you have your loss before split, you have loss of R parent. And then after split, you have loss of R1 plus loss of R2. Right? And if this decrease between your loss of our parent to your loss of your children is not great enough, you might be tempted to say, okay, that question didn't really gain us anything, and so therefore we will not actually use that question. But what I'm saying is that sometimes you have to ask multiple questions, right? You have to ask sort of suboptimal questions first to get to the really good questions, especially if you have sort of interactions between your variables, if there's some amount of correlation between your variables. Okay. So we talked about regularization. I said that we would get to runtime. Let's just go up here again.
Look.
So let's cover that really quickly.
Here, the cube. Oh, here. You cannot see the cube anymore. Disappeared. But it's here actually. And I dip it into my armpit. I like my t-shirt though. Here, it's disappeared.
Okay, so it'll be useful to just find a couple of numbers at this point. So say you have n examples. You have f features. And finally, you have D. Say the depth of your tree is D. Okay. All right. So you have n examples that you trained on. Each has f features, and your resulting tree has depth D. So at test time, your runtime is basically just your depth D. Right? It's just O of D, right? Which is your depth. And typically, though in not all cases, D is sort of is less than the log of your number of examples. And you can sort of think about this as if you have a fairly balanced tree, right? You'll end up sort of evenly splitting out all the examples, sort of recursively like doing these binary splits, and so you'll be splitting it at the log of that end. Okay, so at test time, you've generally got it pretty quick. At train time,
some trees in public garden in Boston.
You have each point.
Like the tree growing up, right? It goes up.
You'll see that each point, right? Once you've done a split, only belongs to the left or right of that split afterwards.
And then comes back
sort of
and goes down.
like this point right here, once you've split
and
here,
there are a
it will
lot
only
of
ever
them
be part of this region. It will never be considered on the other side, on the right-hand side of that
branches
split.
that go down.
Right,
if you look at the squirrels going from one tree to another,
D,
they just go uphill and go downhill.
Each
point. But on these, I've never seen a squirrel go on one of these.
Is part of.
Definitely they go, but like the part here,
nodes.
all of the tree branches, they are upward. So whenever
and then at each node, you can actually work out that the cost of evaluating that point for at train time is actually just proportional to the number of features, f.
And that's good. You don't see squirrels as much on the ground here. In public garden,
I won't get too much into the details of why this is, but you could consider that if you're doing binary features, for example, where each feature is just
in public garden, we don't have any rabbits.
Then you only have to consider
because here
if you have f features total. You only have to consider f
actually
splits.
MIT
so
is the only place I've seen rabbits so much.
And then if it was instead a quantitative,
you have a lot of squirrels. The squirrels are common. Ducks are common. Rabbits are more common here at MIT.
I mentioned briefly that you could sort the overall features and then scan through them linearly. And that also ends up being asymptotically O of f to do that. Okay, so each point is at most O of D nodes, and then the cost of a point at each node is O of f, and you have n points total. So the total cost is really just is just O of n f d, like this. And it turns out that this is actually surprisingly fast, especially
this is super
if you
fast.
consider that n times f is just the size of your original design matrix, right? Or your data matrix, right? Your data matrix
what is f?
Is
features
of size n times f, right? And then your runtime is going through the data matrix at most depth times. And since depth is log of n, that turns out to be, or generally bounded by log of n, you have generally fairly fast train time as well. Any questions about runtime?
D for depth or data?
Okay, so I've been talking a lot about the good sides of decision trees, right? They seem pretty nice so far. However, there are a number of downsides too. And one big one is that it doesn't have additive structure to it. And so let me explain a little bit what that means.
I want to sleep. I slept 6 hours last night. I think the only way out is just hitting the gym.
Okay, so let's say now we have an example.
Power nap.
You have just two
Power
features
nap
again,
is a
so
big
x1,
lie.
x2.
You sleep forever.
And you could say you define a line, okay, just running through the middle, defined by x1 equals x2. And all the points above this line are positive. And all the points below it are negative. Now, if you had a simple linear model, like logistic regression, you'd have no issue with this kind of setup. But for a decision tree,
wow, interesting.
basically, you'd have
regression. It works amazing, and it's like easier regression ever. Decision tree has problem, but decision tree can kind another form of a structure, just these squares here and there, but regression is terrible at it. Interesting. So probably when you want to use a model or machine learning or whatever, you need to look at the data and then choose, or just use all of them and pick one. Like in a two-dimensional space, it really matters how it looks to your eyes, how you can see it, and then you can choose.
have to ask a lot of questions to even somewhat approximate this line. Like what you could try is you could say, okay, let's split it this way, and maybe we can do something this way, and then I'll split here, something like this.
Is it about geometry or
Basically
topology?
something like that, right?
What's the difference between geometry and topology? I want to know that. Like in high school, we had geometry courses about triangles, circles. Even we had analytic geometry, which was about ellipsoids. But wow, you are coding while you start? Really?
Stop reading research papers like this. Googling back and forth while reading takes up more time than you could imagine.
All right, guys, do you want to solve this in 30 minutes? Snag your stocks, I guess. Yeah, but I think geometry, I don't know, in undergrad, I was double majoring in mathematics. I had a topology course, And I think topology and geometry. Topology sounded like about shapes and stuff. I don't know the difference between these two. And we never had well, I never took a geometry course in a, like a, which is geometry is in a rigorous manner. Well, I had a geometry course, sorry, but it was about, yeah, they get super complicated geometry when it wants to be rigorous. It was about complex numbers and these planes. Topology and geometry. Simple. I want something. Who cares about topology? Wow, what is that? I? Okay, this sounds good. Shorter the better.
Jacob Lurie. I'm a professor at Harvard. I've wanted to be a mathematician for as long as I can remember. I guess most of my research is focused on interactions between algebraic geometry and algebraic topology, ways that you can take information from
algebraic geometry and algebraic geometry.
One and get information about the other. Topology is the study of shapes. Algebraic geometry is the study of solutions to polynomial equations. Well, they're both really old fields, and they had a history of interacting in various ways, but the particular thing that I'm interested in is a relatively new one. It's about applying algebraic topology to algebraic geometry by studying equations that you solve up to homotopy in some sense. Well, I would say my favorite story in mathematics is the story of the Weil conjectures. It's a story which also relates algebraic geometry and topology about using topological ideas to count the number of solutions.
Common ground is algebra. It's so simple. You don't need to be at Harvard.
To equations in situations where there are only finitely many. That there's a completely unexpected connection between two different ideas. It's a lot of fun when you find something that you're sure it must be true, but you have no idea why. It's like, you know, an opportunity to really dig into something. I mean, you always hit obstacles, but I'm not sure that I have any non-generic advice to offer about how to get past them. You get past them because you just keep thinking about it until it gives up. You play around with things until you find something that is worth dusting off and sharing with other people. I don't know if it's so hard to hit obstacles, but I'm not sure that I have any non-generic advice to offer about how to get past them. You get past them because you just keep thinking about it until it gives up. You play around with things until you find something that is worth dusting off and sharing with other people. I don't know if it's so hard to decide which ones are worth dusting off, but it can be hard to find one that's worth dusting off. One thing that I think is a real shame is that, say, the introductory math courses that people take when they get to college are in calculus and not sort of elementary number theory or...
Yes, they're in calculus. But if you are in mathematics major, you will have courses in mathematics, I guess. Like in Sharif, it was super easy. You were free to take whatever. Engineering students, they usually take calculus courses because they need it for their future courses, which those courses have no value. They have value. I should not say that. Well, engineering heavily depends on calculus. You cannot be, well, coding and stuff, and these stuff are showing up like in computer science, but engineering definitely, you cannot say I don't want to learn calculus. You can say definitely, but You know what I say, right?
It's a fun area of mathematics that I think a lot of people
Newton, you cannot...
would enjoy if they gave a chance.
That is true.
I have no complaints. It's quite
That
nice
is sad that we don't get to know those other areas, so...
here.
This productivity tool is
Or
Here,
maybe
so you've
not.
asked a lot of questions, and you've only gotten a very rough approximation of the actual line that you've drawn in this case. And so decision trees do have a lot of issues with these kind of structures where the features are interacting additively with one another. Okay, so to recap so far, since we've covered a number of different things about decision trees, there's a number of pluses and minuses to decision trees, okay? So on the plus side, they're actually, I think this is an important point, is that they're actually pretty easy to explain, right? If you're explaining what a decision tree is to like a non-technical person, it's fairly obvious. You're like, okay, you have this tree, you're just playing 20 questions with your data and letting it come up with one question at a time. They're also interpretable. You can just draw out the tree, especially for shorter trees, to see exactly what it's doing. It can deal with categorical variables.
Categorical.
And it's generally pretty fast.
Actually, I didn't get my answer to my question.
However, on the negative side,
oh, it's
something that I
fast.
alluded to was that they're fairly high variance.
I want a simple... simple, intuitive answer. I don't want to... Okay, I know topology. Let's see, introduction to geometry. I also had a course in geometry. Oh, that's too much of intro.
Introduction to the language or some of the characters that we use when we talk about geometry. And I guess the best place to start is to even think about what geometry means. Is you might recognize the first, specify a position. What if we want to move around a little bit more?
Well,
What
this
if
is
that?
high school geometry.
Hey, welcome back.
Why should it have algebraic? Oh, we have algebraic and we have differential. I see.
Hey everybody. Because I wanted to be a theoretical physicist, and so I went to Princeton, and I was a really good student, as I pointed out already. I got A+ on almost everything I had.
The mathematics we learn in school doesn't quite do the field of mathematics justice. We only get a glimpse at one corner of it, but mathematics as a whole is a huge...
Why don't we have geometry?
Through it.
Wow, I'm getting crazy.
What if you could have some kind of online hyperbook that explained...
This is biology.
The mathematics we learn in school doesn't quite do the field of mathematics justice. We only get a glimpse at one corner of it, but mathematics as a whole is a huge and wonderfully diverse subject. My aim with this video is to show you all of that amazing stuff. We'll start back at the very beginning. The origin of mathematics lies in counting. In fact, counting is not just a human trait. Other animals are able to count as well. And evidence for human counting goes back to prehistoric times, with check marks made in bones. There were several innovations over the years, with the Egyptians having the first equation, the ancient Greeks making strides in many areas like geometry and numerology, and negative numbers were invented in China, and 0 as a number was first used in India. Then, in the golden age of Islam, Persian mathematicians made further strides and the first book on algebra was written. Then mathematics boomed in the Renaissance along with the sciences. Now there's a lot more to the history of mathematics than what I've just said, but I'm going to jump to the modern age and mathematics as we know it now. Modern mathematics can broadly be broken down into two areas. Pure maths, the study of mathematics for its own sake, and applied...
There was a series of books that explains everything like in simple ways. Library. I got a game theory one, which I didn't read yet. A very short introduction. Yeah. Let's see if they have geometry as well. Oh, they have! By also, do they have topology? Well, I had a topology course. Yes, they have all of it. Let me add it to my list. Maybe I listen to them in the gym. By the way, if you are at MIT doing geometry and topology, come here and talk with us about this stuff. Yeah, actually I know a guy, but he studies probability theory. Let me text him. Matthew. Is it him? What a photo, nice.
Maths, when you develop mathematics to help solve some real-world problem. But there's a lot of crossover. In fact, many times in history, someone's gone off into the mathematical wilderness, motivated purely by curiosity and kind of guided by a sense of aesthetics. And then they've created a whole bunch of new mathematics, which is nice and interesting, but it doesn't really do anything useful. But then, say, 100 years later, someone will be working on some problem at the cutting edge of physics or computer science, and they'll discover that this old theory in pure math is exactly what they need to solve their real-world problems, which is amazing, I think. And this kind of thing has happened so many times over the last few centuries. It's interesting how often something so abstract ends up being really useful. But I should also mention that pure mathematics on its own is still a very valuable thing to do, because it can be fascinating and on its own can have a real beauty and elegance that almost becomes like art. Okay, enough of this highfalutin. Let's get into it. Pure maths is made of several sections. The study of numbers starts with the natural numbers and what you can do with them with arithmetic operations. And then it looks at other kinds of numbers, like integers, which contain negative numbers, rational numbers like fractions, real numbers, which include numbers like pi, which go off to infinite decimal points, and then complex numbers and a whole bunch of others. Some numbers have interesting properties like prime numbers or pi or the exponential. There are also properties of these number systems. For example, even though there's an infinite amount of both integers and real numbers, there are more real numbers than integers. So some infinities are bigger than others. The study of structures is where you start taking numbers and putting them into equations in the form of variables. Algebra contains the rules of how you then manipulate these equations. Here you'll also find vectors and matrices, which are multidimensional numbers, and the rules of how they relate to each other are captured in linear algebra. Number theory studies the features of everything in the last section on numbers, like the properties of prime numbers. Combinatorics looks at the properties of certain structures like trees, graphs, and other things that are made of discrete chunks that you can count. Group theory looks at objects that are related to each other in, well, groups. A familiar example is a Rubik's Cube, which is an example of a permutation group. And order theory investigates how to arrange objects following certain rules, like how something is a larger quantity than something else. The natural numbers are an example of an ordered set of objects, but anything with any two-way relationship can be ordered. Another part of pure mathematics looks at shapes and how they behave in spaces. The origin is in geometry, which includes Pythagoras, and is close to trigonometry, which I'm sure we're all familiar with from school. Also, there are fun things like fractal geometry, which are mathematical patterns which are scale invariant, which means you can zoom into them forever, and they always look kind of the same. Topology looks at different properties of spaces where you're allowed to continuously deform them but not tear or glue them. For example, a Mobius strip has only one surface and one edge, whatever you do to it. And coffee cups and donuts are the same thing, topologically speaking. Measure theory is a way to assign values to spaces or sets, tying together numbers and spaces. And finally, differential geometry looks at the properties of shapes on curved surfaces. For example, triangles have got different angles on a curved surface. And brings us to the next section, which is changes. The study of changes contains calculus, which involves integrals and differentials, which looks at the area spanned out by functions or the behavior of gradients of functions. And vector calculus looks at the same thing but for vectors. Here we also find a bunch of other areas like dynamical systems, which looks at systems that evolve in time from one state to another, like fluid flows or things with feedback loops like ecosystems. And chaos theory, which studies dynamical systems that are very sensitive to initial conditions. Finally, complex analysis looks at the properties of functions with complex numbers. This brings us to applied mathematics. At this point, it's probably worth mentioning that everything here is a lot more interrelated than I've drawn. In reality, this map should look more like a web tying together all the different subjects, but you can only do so much on a two-dimensional plane, so I've laid them out as best I can.
That was so good. I loved it. Okay.
And brings us to the next section.
What the fuck? Wow, that was amazing. If I had this picture in my head when I was choosing my undergrad major, it would be a big like it would make my decision much easier. Wow, that's crazy. All right. Let's read that book. I don't want to read that book. However, as an armchair theorist, I believe it can be, applied math can be very beautiful, but the problem with a lot of applied math people is that they want to act like a pure mathematicians. No, you should be applied mathematician. I have this feeling. Their culture well, they have differences, right? They try to model real life problems. The missing part is that they don't check if their solutions has any application or not. They don't care about it. A lot of applied math people or CS people who do the theory kind of stuff, including me, the head of mental masturbation department. Actually, we don't have a way to check them. I'm working on Amazon, for example, recommender system. Unless I have a good connection with Amazon and they can implement our ideas, how can we know? I don't know how is it in math. Maybe is it just theory? Even I think in math they should have these theories for something else. Like there should be an application. There should be a question coming from somewhere. Just curiosity. Okay, curiosity is good, but you can have an applied view to math too. I had them. I think I only can listen to them in the gym. I don't want to spend any time on them. And maybe. Oh! Habibi, come in!
Why are you playing on your phone?
We are online, on YouTube.
Are you?
Okay. We got our next podcast. Come on, show your face. Come on! Look at his bicep. Look at his fucking bicep. Ah! You're coming. Promise to our audience here.
I promise to reveal my identity soon.
We are having you for a podcast, right?
Yes.
Promised.
On
Otherwise, you will go to Al Jahannam.
on politics in the Middle East.
Huh?
On politics in the Middle East.
Phonetics?
Politics.
No politics.
In the Middle East.
No. Here we censor everything. All right. We got a guest. I will bring. Okay. Also takes it Matthew to come for geometry versus topology. Let's go. All MITs here. This one. Okay, let's watch the rest of it and we should
which is changes. The study of changes contains calculus, which involves integrals and differentials, which looks at the area spanned out by functions or the behavior of gradients of functions. And vector calculus looks at the same thing but for vectors. Here we also find a bunch of other areas like dynamical systems, which looks at systems that evolve in time from one state to another, like fluid flows or things with feedback loops, like ecosystems. And chaos theory, which studies dynamical systems that are very sensitive to initial conditions. Finally, complex analysis looks at the properties of functions with complex numbers. This brings us to applied mathematics. At this point, it's probably worth mentioning that everything here is a lot more interrelated than I've drawn. In reality, this map should look more like a web tying together all the different subjects, but you can only do so much on a two-dimensional plane, so I've laid them out as best I can. Okay, we'll start with physics, which uses just about everything on the left-hand side to some degree. Mathematical and theoretical physics is a very close relationship with pure maths. Mathematics is also used in the other natural sciences with mathematical chemistry and biomathematics, which look at loads of stuff from modeling molecules to evolutionary biology. Mathematics is also used extensively in engineering. Building things has taken a lot of maths since the Egyptians and Babylonian times. Very complex electric.
My thought on, okay, if you have this section and they're totally separate, it's not as, yeah.
Systems like aeroplanes or the power grid use methods in dynamical systems called control theory. Numerical analysis is a mathematical tool commonly used in places where mathematics becomes too complex to solve completely. So instead you use lots of simple approximations and combine them all together to get a good approximate answers. For example, if you put a circle inside a square, throw darts at it, and then compare the number of darts in the circle and the square portions, you can approximate the value of pi. But in the real world, numerical analysis is done on huge computers. Game theory looks at what the best choices are given a set of rules and rational players, and it's used in economics when the players can be intelligent, but not always, and other areas like psychology and biology. Probability is the study of random events like coin tosses or dice or humans, and statistics is the study of large collections of random processes and the organization.
Applied math? Well, it has a huge application in applied math. But I thought probability is like a pure math.
And analysis of data. This is obviously related to mathematical finance, where you want to model financial systems and get an edge to win all those fat stacks. Related to this is optimization, where you're trying to calculate the best choice amongst a set of many different options or constraints, which you normally visualize as trying to find the highest or lowest point of a function. Optimization problems are second nature to us humans, and we do them all the time, trying to get the best value for money or trying to maximize our happiness in some way. Another area that's very deeply related to pure mathematics is computer science, and the rules of computer science were actually derived in pure maths and is another example of something that was worked out way before programmable computers were built. Machine learning, the creation of intelligent computer systems, uses many areas in mathematics like linear algebra, optimization, dynamical systems, and probability. And finally, the theory of cryptography is very important to computation and uses a lot of pure maths like combinatorics and number theory. So that covers the main sections of pure and applied mathematics. But I can't end without looking at the
about geometry and topology. Fuck that, I don't want to hear this.
And so are oftentimes prone to overfitting your data. They're bad at additive structure. And then finally, they have, in large part because of these first two, they generally have fairly low predictive accuracy. I know what you guys are thinking. I just spent all this time talking about decision trees, and I tell you guys they actually sort of suck. So why did I actually cover decision trees? And the answer is that, in fact, you can make decision trees a lot better through ensembling. And a lot of the methods, for example, the leading methods in Kaggle these days are actually built on ensembles of decision trees. And they really provide an ideal sort of model framework to look at through which we can examine a lot of these different ensembling methods. Any questions about decision trees before I move on? Yeah? I don't think that's strictly, okay, so the question is, for the cross entropy loss, does the log need to be base 2? And the answer is, I'm pretty sure that is not very relevant in this case. I'm not 100% sure about that, but I'm pretty sure that the base of the log doesn't make sense. Cross entropy loss actually initially came out of like information theory, where you have like computer bits and you're transmitting bits. And so it's useful to think in terms of bits of information.
Yeah, TA has knowledge, got knowledge. Look, just guy asked about information theory, and just, yeah, I know the shit.
Pretty sure that the base of the log doesn't make sense. Cross entropy loss actually initially came out of like information theory, where you have like computer bits and you're transmitting bits. And so it's useful to think in terms of bits of information that you can transmit, which is why it came up as log base 2 in the initial formulation. Okay, so now let's talk about ensembling. Okay, so why does ensembling help? At some level, you can sort of think back to your basic statistics. So say you have xi's, which are random variables. I'll sometimes write this as just RV, that are independent, identically distributed. And so probably a lot of you are familiar with this already, but you can call this IID. Okay? Now say that your variance of one of these variables is sigma squared. Then what you can show is that the variance of the mean of many of these variables, so of many of these random variables, or written alternatively, 1 over n sum over i's of xi, is equal to sigma squared over n. And so each independent variable you factor in is decreasing the variance of your model. Right? And so the thought is that if you can factor in a number of independent sources, you can slowly decrease your variance. Okay, so I've sort of, though this is a little bit simplistic of a way of looking at this, because really all these different things you're factoring together have some amount of correlation with each other. And so this independence assumption is oftentimes not correct.
What a t-shirt.
So if instead you drop the independence assumption.
Drop it. Oh, shit. Well, then it can be sigma squared.
So now your variables are just ID, right?
If they're all equal. Can it be bigger? Can it get bigger?
And say we can characterize what the correlation between any two xi's is. And we can write that down as rho.
I don't think so.
X's. Then you can actually write out the variance.
Then you can actually write out. Then you can actually do that. Then you can actually be
as
sigma
squared plus 1 minus rho over m, or no, n, squared. Okay? And so you can sort of see that if they're fully correlated, then this term will drop to 0, and you'll just have sigma squared again, because adding a bunch of fully correlated variables is just going to give you the original variable's variance. Versus if they're completely decorrelated, then this term drops to 0, and you just end up with sigma squared over n, which gives you the initial independent, identically distributed equation. And so in this case, really what you want to do, the name of the game is you want to have as many different models that you're factoring as possible to increase this n, which drives this term down. And then on the other hand, you also want to make sure those models are as decorrelated as possible so that your rho goes down in this
Rho
first
goes
term.
to 0 and n goes to infinity.
Okay.
All right, sounds good. Decorrelated, more independent, and bigger sample.
And so this gives rise to a number of different ways to ensemble. And one way you could think about doing this is you just use different algorithms. Right? This is actually what a lot of people in Kaggle, for example, will do, is they'll just take a neural network, a random forest, an SVM, average them all together, and generally that actually works pretty well, but then you sort of have to spend your time implementing all these separate algorithms, which is oftentimes not the most efficient use of your time. Another one that people would like to do is just use different training sets.
Okay. Ensemble.
Okay. And again, in this case, like you probably spend a lot of effort collecting your initial training set. You don't want your machine learning person to just come and recommend to you that just go collect a whole second training set or something like that to improve your performance. Like that's generally not the most helpful recommendation. Okay? And so then what we're going to cover now are these two other methods that we use to do ensembling. And one of them is called bagging, which is sort of trying to approximate having different training sets. I'll get into that quickly. And then you also have boosting. And just so that you guys will have a little bit of context, we're going to be using decision trees to talk a lot about these models. And so bagging, you might have heard of random forest.
Boosting or boostring?
That's a variant of bagging for decision
that
trees.
was what is string?
And then for boosting, you might have heard of things like add a boost,
bootstrap,
or XGBoost.
Oh, XGBoost! I worked with XGBoost in Clubhouse. We had it.
A variant of boosting for decision trees.
Bagging is random forest.
Okay, so that sort of covers at a high level what we'd want to do. These first two are very nice because they sort of would give us a much more independently correlated or less correlated variables. But generally we end up doing these latter two because we don't want to collect new training sets or train entirely new algorithms. Okay, so let's cover bagging first. Okay, so bagging really stands for this thing. It's called bootstrap aggregation. Okay. And so first, let's just break down this term. So bootstrap, what that is it's typically this method used in statistics to measure the uncertainty of your estimate. Okay?
Oh, I said bootstrap! Wow!
So
Totally randomly, they just... Wow.
Okay, so bagging really stands for this thing. It's called bootstrap aggregation.
So fun. What's Bootstrap?
And so first, let's just break down this term. So Bootstrap, what that is it's typically this method used in statistics to measure the uncertainty of your estimate, okay? And so what is useful to define in this case for when you're talking about bagging is you can say that you have a true population P, okay? And your training set S is sampled from P, right? So you just are drawing a bunch of examples from P, and that's what forms your training set at some level. And so ideally, like for example, this different training sets approach, what you do is you just draw S1, S2, S3, S4, and then train your model in each one of those separately. Unfortunately, you generally don't have the time to do that. And so what bootstrapping does is you assume basically that your population is your training sample, okay? So you assume that your population is your training sample. And so now that you have this S is approximating your P, then you can draw new samples from your population by just drawing samples from S instead, okay? So you have bootstrap samples, is what they're called. Z sampled from S. And so how that works is you basically just take your training sample, okay, say it's of like cardinality n or something, and you just sample n times from S.
Okay, what the fuck, really? Something that I had to listen to, I didn't listen to.
Estimate.
I was inviting another
person.
person.
So bagging really stands for this thing, it's called bootstrap aggregation. Okay.
No phone, no phone.
And so first, let's just break down this term. So bootstrap, what that is it's typically this method used in statistics to measure the uncertainty of your estimate, okay? And so what is useful to define in this case for when you're talking about bagging is you can say that you have a true population P, okay? And your training set S is sampled from P, right? So you just are drawing a bunch of examples from P, and that's what forms your training set at some level. And so ideally, like for example, this different training sets approach, what you do is you just draw S1, S2, S3, S4.
Bootstrap actually have a true population P training set.
And then train your model in each one of those separately. Unfortunately, you generally don't have the time to do that. And so what bootstrapping does is you assume...
He's like, unfortunately, you didn't have enough time to do that.
Basically, you generally don't have the 2, S3, S4, and then train your model in each one of those separately. Unfortunately, you generally don't have the time to do that.
Don't have the time.
And so what bootstrapping does is you assume basically that your population is your training sample.
Why are men lads so shy? Why are people so shy to come?
Okay? So you assume that your population is your training sample. And so now that you have this S is approximating your P, then you can draw new samples from your population by just drawing samples from S instead. Okay? So you have bootstrap samples, is what they're called. Z sampled from S. And so how that works is you basically just take your
Honestly, I'm okay. Let me send him the video so that he knows you're. Okay. Nope. Oh.
your training sample, okay, say it's of like cardinality n or something, and you just sample
We are
n times
recording.
from S.
Ashkan, come here.
You do it with replacement, because they're pretending that this is a population, and so doing it with replacement sort of makes that assumption hold, that you're sampling from it as a population. Okay, so that's bootstrapping. So you generate all these different bootstrap samples, Z, from your training set. And what you can do is you can take your model and train it on all these separate bootstrap samples.
Mm-hmm.
And then you can sort of look at the variability and the predictions that your model ends up making based on these different bootstrap samples. And that gives you sort of a measure of uncertainty. I'm not going to go into too much detail on that because that's not actually what we're going to use bootstrapping for. What we want to use bootstrapping for is we want to aggregate, basically, bootstrap samples. And so at a very high level, what that means is we're going to take a bunch of bootstrap samples, train separate models on each, and then average their outputs. Okay? So let's make that a little bit more formal. So you have bootstrap samples.
I already lost.
Z1 through Zn, say. Okay, capital N. That's just say how many bootstrap samples you're going to take. Okay, you train a model, Gm.
Okay, these are new, guys. I have to pay attention.
Zn.
Pay attention. Pay attention.
Okay? And then all you're doing is you're just defining this new sort of meta model. I'm not putting a subscript on this one to show that it's the meta model, G of M, which is just the sum of your predictions of your individual models divided by the total number of models you have.
M.
And this is just writing out what I was sort of talking about right up there for bagging. You're taking these bootstrap samples, and then you're training separate models, and then you're just aggregating them all together to get this bagging approach.
How do they make the bootstrap?
And so if we just do a little bit of analysis from the bias variance perspective on this, we can sort of see why this kind of thing might work. And so you'll recall we have this equation up here, right? The variance of the mean is rho sigma squared plus 1 minus rho over n of sigma squared. So let me just write that out here to be clear. And in this case, our m is actually really just the number of bootstrap samples, so we'll just use big M in this case.
What is rho? Is it?
And what you're doing is by taking these bootstrap samples, you're sort of decorrelating the models you're training. You're bootstrapping.
He didn't say how we bootstrap though.
Is driving down.
Rho.
Okay. And so by driving this down, you're sort of making this term get smaller and smaller. And then your question might be, okay, what about this term here? And it turns out that basically you can take as many bootstrap samples as you want, and that'll slowly drive down, it increases M and drive down this second term. And it turns out that one nice thing about bootstrapping is that increasing the number of bootstrap models you're training doesn't actually cause you to overfit any more than you were beforehand. Because all you're doing is you're driving down this term here. So more M.
No, nothing.
Is just less variance, right? All you're doing is driving down the second term as much as possible when you're getting more and more bootstrap samples. So it generally only improves performance. And so generally what people will do is they'll sample more and more models until they see that their error stops going down, because that means they basically eliminated this term over here. So this seems kind of nice, right? You're decreasing the variance. Where's the trade-off coming in? Oh, there's a question.
Sharp eyes.
Yeah, there's definitely a bound, right? Because I'm not going to define one formally right now. Oh, the question is, can you define a bound on how much you decrease rho by? Yeah, so there's definitely a lower bound, a lower bound on how far you can decrease rho. Basically, it comes down to your bootstrap samples are still fairly highly correlated with one another. Right? Because you're still just drawing it from the same sample set S.
Really, I like that.
Your Z is going to end up containing about each Z is going to contain about 2/3 of S. And so your Z's are still going to be fairly highly correlated with each other. And though I don't have a formal equation to write down as to exactly how much that decreases rho by, or how much that bounds rho by, you can sort of see intuitively that there is a bound there, and that you can't just magically decrease rho all the way down to 0 and achieve 0 variance. So I was saying that you decrease variance. This seems very nice. One issue that comes up with bootstrapping is that in fact you're actually slightly increasing the bias of your models when you're doing this. And the reasoning for that...
Bias, we started to remove variance and now we fucked up the balance? No, bias. I forgot.
Is because of this subsampling that I was talking about here. Each one of your Z's is now about 2/3 of the original S. So you're training on less data, and so your models are becoming slightly less complex, and so that increases your bias in this case. Yes? Yeah, for sure.
Yeah, for sure.
So the question is, can you explain the difference between a random variable and an algorithm in this case, right? And so you can sort of, at a very high level, you can think of an algorithm as a classifier, as a function that's taking in some data and making a prediction, right? And if you sort of see that whole setup as sort of like the algorithm as giving some sort of output in a probabilistic perspective, you can sort of see the algorithm as like a random variable in this case. Sort of like, you're basically considering sort of the space of possible predictions that your algorithm can make. And that you can sort of see as a distribution of possible predictions, and that you can approximate that as a random variable. I mean, it is a random variable at some level, because it's sort of like based on what training sample you end up with, your predictions of your output model are going to change. And so since you're sampling sort of these random samples from your population set, you can consider your algorithm as sort of based on that random sample, and therefore a random variable itself. Okay, so yeah, your bias is slightly increased because of random subsampling.
Vietnam, made in Vietnam.
But generally, the decrease in variance that you get from doing this is much larger than the slight increase in bias you get from doing this randomized subsampling. So in a lot of cases, bagging is quite nice.
No.
Okay?
Finish it. Bootstrap.
Okay, so we've talked a bit about bagging. Let's talk about decision trees plus bagging now.
Bagging doesn't sound nice.
Okay, so you recall that decision trees are high
Loop at the back of a boot. Oh.
Low bias. Okay. And this right here sort of explains why they're a pretty good fit for bagging. Okay, because bagging, what you're doing is you're decreasing the variance of your models for a slight increase in bias. And since most of your error from your decision trees is coming from the high variance side of things, by sort of driving down that variance, you get a lot more benefit than for a model that would be on the reverse, high bias and low variance. Right? So this makes this like an ideal fit for bagging.
What about reboot? Is it also from boot? Reboot.
Okay, so now this is sort of decision trees plus bagging. I said that random forests are sort of a version of decision trees plus bagging. And so what I've described here is actually almost random forests at this point. The one key point we're still missing is what from your variance that you get from doing.
Shut down and restart. Nothing. How is related to boot? This set of initiating punch cards was called bootstrap cards. Thus, a cold start was called booting the computer up. If the computer crashed, it was rebooted. So it's like reboot strap.
Doing this is much larger than the slight increase in bias you get from doing this randomized subsampling. So in a lot of cases, bagging is quite nice. Okay?
Finish.
Okay, so I've talked a bit about bagging. Let's talk about decision trees plus bagging. Okay, so you recall that decision trees are high variance.
Mm-hmm.
Low bias.
Bias.
And this right here sort of explains why they're a pretty good fit for bagging. Okay, because bagging, what you're doing is you're decreasing the variance of your models for a slight increase in bias. And since most of your error from your decision trees is coming from the high variance side of things.
Decision trees, high variance, low variance. Bootstrap, high bias, low variance, right?
By sort of driving down that variance, you get a lot more benefit than for a model that would be on the reverse, high bias and low variance. Right? So this makes this like an ideal fit for bagging.
People teach in Stanford for 10 weeks. No mathematics, no proof.
Okay, so now this is sort of decision trees plus bagging. I said that random forests are sort of a version of decision trees plus bagging. And so what I've described here is actually almost random forests at this point. The one key point we're still missing is that random forests actually introduce even more randomization into each individual decision tree. And the idea behind that is that as I had that question from before, is this row, you can only drive it down so far through just pure bootstrapping. But if you can further decorrelate your different random variables, then you can drive down that variance even further, okay? And so the idea there is that basically at each split for random forests, you consider only a fraction of your total features, right? So it's sort of like, for that ski example, maybe like for the first split, I only let it look at latitude. And then for the second split, I only let it look at the time of the year. And so this might seem a little bit unintuitive at first, but you can sort of get the intuition through two ways. One is that you're decreasing rho. And then the other one is you can think that, say you have a classification example where you have one very strong predictor that gets you very good performance on its own. And regardless of what bootstrap sample you select, your model is probably going to use that predictor as its first split. That's going to cause all your models to be very highly correlated right at that first split, for example. And by instead forcing it to sample from different features instead, that's going to increase the, or decrease the correlation between your models. And so it's all about decorrelating your models in this case.
Decorrelating your model.
Okay, and that sort of brings to a close a lot of our discussion of bagging. Are there any questions regarding bagging? Okay. Now I've covered bagging, let's get a little bit into boosting.
Dude, time is over. Give yourself.
And I'll make this quick, but basically, whereas bagging, we sort of saw in the intuition that we were decreasing variance, boosting is sort of actually more of the opposite, where you're decreasing the bias of your models, okay? So.
Bagging and boosting.
And also, it's basically more additive in how it's doing things. So versus, you'll recall that for bagging, you were taking the average of a number of variables. In boosting, what happens is you train one model, and then you add that prediction into your ensemble. And then when you train a new model, you just add that in as a prediction. And so that's a little bit hand-wavy right now, so let me actually make that clear through an example.
So boosting is against bagging, decreases bias, added.
So say you have a data set, x1, x2.
And adds to decision trees are not additive.
And you have some data points, maybe some, let's actually just call
them
pluses and minuses. So you have some more pluses here, and then maybe a couple minuses, and then some pluses here. Okay? And what you say you're training size 1 decision trees, so decision stumps is what we call them. It's you only get to ask one question at a time. And the reason behind this, just really quickly, is that because you're decreasing bias, by restricting your trees to be only depth 1, you basically are increasing their amount of bias and decreasing their amount of variance, which makes them a better fit for boosting kind of methods. And say that you come up with a decision boundary, okay, say this one here. Okay? And what you're going to do is on this side, you predict positive, right? And on this side, you predict negative. This is like a reasonable line that you could draw here. But it's not perfect, right? You've made some mistakes. And in fact, what you can do is you can sort of identify these mistakes. So if we draw this in red, right, you've made these guys as mistakes. And what boosting does is basically it increases the weights of the mistakes you've made. And then for the next decision stump that you train, it's now trained on this modified set, which we can, let's just draw it over here. And so now these positives, I'll just draw them much bigger. You know, you've got big positives here and some small negatives and some small positives, some big negatives here. And so now your model, to try and get these right, might pick a decision boundary like this, right? And this is also basically recursive in that each step, right, you're going to be reweighting each of the examples based on how many of your previous ones have gotten it wrong or right in the past. And so basically what you're doing is you can sort of weight each one of these classifiers. You can determine for classifier GM a weight alpha M, which is proportional to how many examples you got wrong or right. So a better classifier, you want to give it more weight, and a bad classifier, you want to give it less weight. Proportional. And I think that the exact equation used in AdaBoost, for example, is just log of 1 minus the error of your mth model divided with, basically log odds. Okay? And then your total classifier is just f of x, or let's just call it g of x again. G of x is just the sum over m of alpha m g of m. Okay? And then each g of m is trained on a weighted, on a reweighted, actually, reweighted training set. And so I've glossed over a lot of the details here in interest of time, but the specifics of an algorithm like this will be in the lecture notes. And this algorithm is actually known as AdaBoost. And basically, through similar techniques, you can derive algorithms such as XGBoost or gradient boosting machines that also allow you to basically reweight the examples you're getting right or wrong in this sort of dynamic fashion, and slowly adding them in this additive fashion to your composite model. And that about finishes it for today. Thanks for coming. Yeah, have a great rest of your week.
Enough, guys. I'm tired, to be honest. I'm dead. Control Shift 1. I am dead. Have a good night. Enjoy the rest of your Monday. You can watch it on Tuesday up to Sunday. I will keep it for you online. Grab a glass of wine.